Our first presenter for this session is Ethan Epperly. His field is applied in computational mathematics. He's from the California Institute of Technology and performed his practicum at Lawrence Berkeley National Laboratory in 2021. And today he will be speaking about randomly pivoted Cholesky faster matrix approximation for scientific machine learning.
Thank you very much for the introduction, and thank you to all of you for being here. Today I'm going to be speaking about randomly pivoted Cholesky, faster matrix approximation for scientific machine learning. And this is joint work with my friends and colleagues, Yifan Chen, Rob Weber, and Joel Trop. All right. So at the broadest possible level, this talk is about the following challenge that we face in 21st century computational science. We have a lot of data. You run a supercomputer for a long time. It produces lots and lots of scientific data, and we need scalable methods to process and analyze that data. And in the 21st century, that means machine learning methods. And so to motivate the algorithms that I'm going to talk about in this talk, I want to begin with a concrete application in computational biochemistry. So a fundamental problem in computational biochemistry is to understand the metastable or long-lived configurations of a biomolecule, a large biomolecule like a protein. And a real fundamental tool for this task are molecular dynamics simulations, which can be used to simulate the motion of biomolecules over short time intervals. But there remains a question of how do we interpret and understand this MD data? And that brings the question, what is a programmatic, scalable, and reliable way of identifying metastable states from molecular dynamics data sets? So there's a number of different methods. I won't talk about all of them, or I'll only talk about one of them. But spectral clustering remains a very popular method for this problem. And I'll just briefly describe it to you now. So we begin by collecting snapshots of our protein or other biomolecule at n equally spaced times. Now, the real kind of conceptual trick of this algorithm is to then take these n data points and assemble them into an n by n similarity matrix. And by a similarity matrix, I just mean that if I look at row I and column j of this matrix, so the aij entry, that's going to be some quantitative measure of the similarity of the state at time I to the state at time j. And similarity here can be measured by a user-specified positive definite kernel function. So most people aren't very creative. They just pick a standard functional form like a Gaussian kernel. All right? So yeah, you take your data set of size n, you blow it up to this n by n similarity matrix. And to actually get the metastable configurations, you start off by computing the first few eigenvectors of the similarity matrix. So we have this big n by n matrix, and we now compute from it a much thinner matrix, V, consisting of the eigenvectors of A. And we'll remember that every row of this matrix corresponds to one of our snapshots, to one of our states. And so in order to extract metastable configurations, we now can apply a general purpose clustering algorithm, such as k-means, to the rows of this eigenvector matrix. And in this stylized cartoon I have here, we've identified two metastable configurations, configuration 1, configuration 2, which for instance could represent folded and unfolded states of a protein. All right. So spectral clustering is a widely used and effective technique in biochemistry. And I think it's so widely used because it's very simple, robust, and user-friendly. So you don't need to tune any parameters. You don't need a whole neural network or something that a scientist might not know how to use. It's just simple. Form the similarity matrix, compute the eigenvectors, cluster them. All right, and so this approach is widely used, but kind of the hello world first example that you would test out on is this alanine dipeptide molecule. It's a tiny little molecule by the standards of modern computational biochemistry. But you can apply spectral clustering to MD simulation data, and you get a nice plot like this. And so we see we've identified a number of different metastable configurations. All right, and there are many uses of spectral clustering beyond biochemistry. So if you have any scientific data set of n items, you can use spectral clustering to group them into scientifically relevant groupings. All right. So unfortunately, this is a widely used and very popular approach, but it has a fundamental limitation, which is that I've taken a data set of size n, and I've blown it up into a similarity matrix of size n by n equals n squared. And so directly implementing spectral clustering is very computationally costly. The memory is going to scale like n squared, because I have to store this n by n similarity matrix. And if I just use eig in MATLAB or eigh in NumPy to compute the eigenvectors of this matrix, that's going to require n cubed operations. And so these 1-2 punch of high memory and high time really limits spectral clustering to being useful for moderately large data sets, perhaps 100,000 if you're really pushing it. And this scalability limitations of spectral clustering places real limits on how actual scientists can use the method. So routinely, scientists will discard over 99% of their data just so that it's small enough to apply spectral clustering to, after which it still takes hours or days of computation on a dedicated workstation. So clearly, there must be a better way, and indeed, there is. So, I'm going to tell you about an algorithm, randomly pivoted Cholesky, that can speed up spectral clustering and other scientific machine learning algorithms significantly. All right, so our core computational tool is a method called low-rank approximation. And really, our goal for this technique is to reduce the memory and runtime of spectral clustering and other scientific machine learning algorithms to scale linearly in the number of data points n. All right. So a low-rank approximation is a way of compressing a large matrix into a more memory-efficient, smaller, compressed representation while preserving accuracy. All right. So the idea is to take this big n by n matrix A and approximate it as a product of two smaller matrices, F and F transpose. And in particular, we're going to choose this smaller matrix F to have k columns, where k is much, much smaller than n, maybe 100 or 1,000. And in so doing, we're going to reduce the storage. Instead of storing this big n by n matrix, we're now going to store this n by k, like n by 100 or n by 1,000 matrix. And so now F, the number of parameters in F scales linearly in the size of the data set. So this is great. But there's kind of a paradox or a real challenge in actually using this low-rank approximation strategy, which is that we're trying to approximate all n squared numbers in this n by n array, but we want algorithms that scale only linearly in n. So in particular, we want an algorithm that's going to approximate all n squared entries in A that only looks at a small fraction of the entries. Because if I want an algorithm that has a runtime scaling like n, I can't even look at all n squared entries in that runtime budget. So this seems like a kind of an impossible algorithmic task, but surprisingly, it's not. All right, so my colleagues and I, we developed this randomly pivoted Cholesky algorithm, which provably produces a near optimal low-rank approximation to any n by n similarity matrix. And it does so with a runtime that scales linearly in the number of data points n. And really, this algorithm is a simple combination of two ideas, one of them classical and one of them modern. So the classical idea is a so-called pivoted Cholesky decomposition, which has been used to compute low-rank approximations to matrices since the 80s. The real thing that our algorithm does that supercharges this classical idea is combining it with a modern idea of randomization. The idea that sometimes the performance of an algorithm can be improved by allowing the algorithm to make random choices. All right, so this is the most technical slide of the talk. Here is the actual algorithm. For those of you familiar with linear algebra and Gaussian elimination and such things, the idea of the algorithm is to perform k steps of Cholesky factorization, also known as Gaussian elimination, using a randomly selected pivot entry at every step. All right, so more specifically, step one of the algorithm, we're going to look at the diagonal of the matrix. And the diagonal is going to kind of tell us how important each entry of the matrix is. So if a diagonal entry is very large, that's important, and we should pick it more often. Right. All right, so we're basically going to look at the diagonal, and we're going to pick a diagonal entry proportional to its size. And we're going to use that as our pivot entry for Gaussian elimination. We're going to eliminate it from the matrix and add whatever we take away to the approximation. All right. And so this is not an efficient implementation of this algorithm, but with an efficient implementation, this is going to run scaling linearly in n, which is exactly what we wanted. And really, I should stress the key innovation of our approach is this random pivot selection rule. And we can prove as a theorem that this randomly pivoted Cholesky algorithm produces a near optimal low-rank approximation in the sense I've written on this slide. And this is not just an empirical observation, it is a proven fact of mathematics. I should stress that this algorithm is only applicable to so-called positive semi-definite similarity matrices, which is the case for our spectral clustering example, but might not be the case for whatever your data matrix looks like. All right, so let me show you how this algorithm works in practice. So we saw spectral clustering earlier in the talk. And when we apply randomly pivoted Cholesky to accelerate spectral clustering, we get something like this. So we correctly identify the 4 different metastable configurations of alanine dipeptide. And a nice thing about this algorithm is each data point represents, each pivot selected by the algorithm is a data point, and you can just plot the pivots selected by the algorithm on the plot with the clusters, which we've done in these black dots. And we see that randomly pivoted Cholesky nicely produces pivots distributed between all of the clusters. But really, the most important thing, this algorithm has reduced hours or days of computation to seconds of computation on a laptop. So it really has sped things up dramatically. I haven't talked about competitor methods, but I'll just briefly mention that there are 2 other algorithms you might consider. And you see that they both have failure modes. Neither of them correctly identifies the clusters. And it's because this greedy method puts the pivots in sparse regions of data space where they're not very helpful. And this uniform method basically entirely misses a cluster. So randomly pivoted Cholesky is really the Goldilocks between these 2 previous algorithms, achieving a good distribution of pivots across all the clusters. Now, randomly pivoted Cholesky is not just a method for spectral clustering. If you have any scientific machine learning algorithm that is based on a positive semi-definite similarity matrix, so Gaussian process regression, kernelized SVM, you can use randomly pivoted Cholesky to accelerate it. And it's been really exciting over the past several years to see a growing body of different papers in different areas of science and machine learning applying randomly pivoted Cholesky to different scientific problems. All right, I'll briefly mention high-performance computing considerations. The existing RP Cholesky algorithm is fast, but could be made faster. And to address this, we have a new algorithm that is in preparation, which processes columns in blocks, leading to speedups of up to 100 times over the basic randomly pivoted Cholesky method, which processes columns 1 at a time. All right. And a high-performance implementation of a version of randomly pivoted Cholesky is underway at Sandia National Labs by my friend and colleague, Riley Murray, as part of the DOE-supported Randall APAC software project. All right, so to conclude, many scientific machine learning algorithms, such as clustering for biochemistry, are based on a similarity matrix. Storing and manipulating this n by n similarity matrix leads to significant scalability limitations. Randomly pivoted Cholesky is a fast way of producing a provably near-optimal low-rank approximation to these matrices, leading to significant speedups for many scientific machine learning algorithms. And so I want to conclude by asking, There's a lot of people in this room. I'm sure many of you use methods based on these kind of similarity matrices. Could randomly pivoted Cholesky help speed up your research? And with that, I'd like to thank you all for your time. I'd like to extend my thanks to the DOE CSGF for the years of support, and definitely the staff at Krell for all they've done. So thank you all very much for your attention, and I'm happy to take questions.